Good morning, everyone. I'm very happy to introduce our speaker today, Dr. Maria Nikolinakou. Maria is a research professor at the Bureau of Economic Geology, Jackson School of Geoscience, and she is a geotechnical engineer. Maria received her master and PhD degree in theoretical soil mechanics from MIT and her diploma in civil engineering from the National Technical University of Athens, Greece. Before joining the Jackson School, she worked for Shell in reservoir depletion geomechanics. Her research focused on studying the coupled hydromechanical behavior of large-scale geological systems, such as salt and thrust belts. She is currently the president of American Rock Mechanics Foundation and associate editor in Rock Mechanics, Rock Engineering Journal. And with that, let's welcome Maria.
Thank you. I'm on, right? Yes. Well, thank you for having me in the UTIG seminar. And today I will talk about the mechanisms that generate overpressure in the shallow parts of subduction zones and some implications both for compaction of the sediments and also for the strength of the plate interface. As Kehua mentioned, I'm a geotechnical engineer, and before joining the Jackson School 15 years ago, my research revolved around the construction of a metro, deep excavations, the constitutive behavior of a tropical soil, and to the great frustration of my PhD supervisors, the structural stability of flying buttresses. So with this background, I hope you allow me to start the talk with a very kind of high-level figures about subduction zones. I'm sure all of you in this room know more about these systems than I do. What draws me in these areas is this hydromechanical coupling between the tectonic loading and then the changes in stresses and deformation, and how the fundamental level research that we do can help understand better the mechanism behind earthquakes. So going back, the subduction zones and their mechanics have been studied for several decades. Even from the early 19th, there was an understanding that this is an evolving system where we have material that enters the thrust zone. And while this is happening, we have a change in the deformation patterns. It was also understood that there is a lot of generation of overpressures and also dissipation of these pressures, not only through faults, but also through the matrix. And then last but not least, that we have a significant change in the stress state in the system. We start seaward, where it's basically the case of a uniaxial burial, where the maximum principal stress is vertical, and everything pretty much depends to what happens to the overburden. And then we go through the trench, the stress state rotates, and then inside the wedge, we have a case of compressional failure or Coulomb failure, where now the maximum principal stress is sub-horizontal. In contrast, if we look at the footwall, things remain pretty much at a uniaxial state during the subduction. So a long-standing question here is, how does this change in the stress state from burial to frictional failure affect things like the overpressures, dewatering, or the strength of the plate interface? And the community has tried to address this question over several with several methods and over several scales. For example, and this is not intended to be exhaustive, seismic or geophysical data can give us some understanding or what's the state of compaction or overpressure in the ground. And I have here a case study from Nankai. The general area shown here on the right. And then the plot here on the top left is compressional velocities. Here is this white line indicates the location of the décollement. And we see how there are velocities that are lower, above, or near the décollement. And this has been interpreted to reflect high overpressure. Staying with the field, but at a local scale, borehole information can also give us an understanding of what is the physical properties in parts of the systems. Another case, again from Nankai, I show here a borehole seaward of the trench. There's a borehole inside the wedge. We have plots of porosity below with depth, and we see that the sediments inside the compressional wedge are now more compacted than the footwall sediments. So in a sense, this basically reflects that there is a contrast in physical properties between the hanging wall and the footwall. And actually, where we stand in terms of field observations, and that's sort of the state of the field that several people in this room are leading, is that we can now get localized measurements at a really small scale at a borehole, but relate them to a much larger scale and observations such as like earthquakes or fault slip. Other than field work, there's been obviously like decades of numerical modeling, and these models have tried to address from simple to very complicated ways how pressures change and how these large deformations and this change in the stress state affect the overpressures. So where do we fit in this picture? So our contribution is that we've developed large strain evolutionary geomechanical models that couple deformation with porous fluid flow. And most importantly, they bring in realistic sediment rheology that is able to capture the poroplastic behavior of marine sediments. And specifically, this addresses the fact that both mean and differential stresses can generate overpressures. So over the next 30 minutes or so, I'm going to use these large strain models and explain how overpressures can develop in these zones. And if you want to read further, we published a paper on this in JGR in 2023. So because the sediment rheology is at the core of what we're doing, I have here a couple of slides just to give you an understanding of what is this sediment behavior framework. And I start with a set of axes that we have the average stress in the horizontal, that's vertical plus horizontal divided by 2, and differential stress at the vertical, difference between the two. We are bounding the permissible state of stresses with these critical state lines that at a high level is an equivalent of the more Coulomb failure criteria. And the other lines I have here is these contours that I term isoporosity, and they're basically a combination of stress states that have the same porosity value. And what this tries to illustrate that is in this framework, we have an interrelationship between mean stress, shear stress, and porosity. So let's see, for example, what happens to a sediment that starts seaward and subducts in the footwall. So we go from the black to the blue. It starts on a uniaxial stress state. This loading remains pretty much uniaxial. The only critical thing that happens here is that we move to a different isoporosity line because we're now under higher overburden. In contrast, if you look at a point at the hanging wall, what happens here is we increase the horizontal stress. Therefore, this vertical axis here becomes negative, and we go all the way down and fail in this negative state with a different isoporosity line. Now, to bring in a little bit more this interrelationship with porosity, I'm going to generalize this figure. We are now looking at the same figure, but we have an overall mean stress here. So this includes sigma 2, the out of plane, and the overall Mises deviatoric stress, which is always positive. And so our path stays in the positive side and fails here. And then below, we cross-plot porosity, and we see that during this path, as we cross over the trench and get into the subduction, into the wedge, we experience compaction and we end up at a lower porosity value. Now, what is critical of this formulation is that if we had the same change in mean stress over a uniaxial path, we would have had a much less change in porosity. And the reason for that is because shear stresses also contribute to compaction. In a sense, at a very high level, you can think that you have a assembly of little grains, and if you just shear it, you will help them rearrange in the microstructure. So what do we get out of all this detour? Is the fact that we interrelate mean, shear, and porosity, and mean and shear both contribute to porosity loss or overpressure. So let's move with a geomechanical model now. I show here some high-level details about this model. We have a sediment layer of about 5 kilometers with a décollement at the 3-kilometer depth. We simulate the tectonic loading by moving this backstop at a total distance of 85 kilometers with a rate at the base model of 5 millimeters per year. We use the finite element program ELFEN. This is 2D plane strain models. The analyses are transient, so we couple the formation with drainage and compaction. And as I mentioned, we use a critical state formulation to describe sediment rheology. So I'm going to play a movie that shows how the formation occurs. And on top of it, we have contours of overpressure, which is, just to remind you, the overall pressure minus hydrostatic pressure. So we start moving the backstop. We pretty quickly establish a critical wedge. And then you see how, as we get into the model area here, we generate overpressures both in the hanging wall and then in the footwall. So just snapshots out of this movie so we can look at them with more peace. The important high-level thing here is that we interrelate this deformation with changes in stress and pore pressure. And that's a key feature of this approach, is that we not only generate overpressures, we predict the full stress tensor, but also the full strain tensor. And what better way to illustrate that than to basically follow the strain ellipses as sediment gets abducted. So these are ellipses that are drawn based on exports from the numerical model. And I summarize here below pretty much what happens in the hanging wall and in the footwall. And we see that seaward, we have this ellipse with characteristics of burial, where the vertical axis is more compressed than the horizontal. Then we rotate in the wedge, in the trench. And then we have a rotated, compressed in the subhorizontal axis ellipse inside the wedge. And below, in the footwall, as expected from the change in the stress state, we have a strain ellipse that stays pretty much uniaxial. What's exciting about this is that we are now having numerical results that are actually mechanically quantify strain observations that have been made in the field. Or we are simulating observations at this fabric scale. The feature of this presentation is overpressure. So I'm bringing back here contours of the overpressure to make 3 key points out of this result. We have overpressures that start seaward of the trench. They increase quickly in the trench area, and they are higher in the hanging wall than they are in the footwall. To convince you a little bit more about the last point, I take here a vertical profile. We plot overpressure with depth. Overpressure is the blue line. The black is the reduced overburden. And we see how in the hanging wall, even 10 kilometers into the wedge where I took this profile, we have overpressures higher than the footwall. Another way to look at overpressures is the overpressure ratio lambda star. And I bring this in because it helps us understand how overpressures change relatively to the change in overburden. So the figure on the top right just shows you the definition of lambda star. We have the hydrostatic profile, pore pressure in blue, vertical stress is in orange, and lambda star is defined as the difference between pressure minus hydrostatic, overburden minus hydrostatic. So if both pressure and overburden are changing at the same rate, this lambda star wouldn't vary much. What we see here is that it starts increasing seaward of the trench and increases really fast in the trench area. And what this tells us is that there must be a mechanism other than overburden that generates overpressures. Obvious candidate here is the mean stress. Mean stress increases in the systems because we apply this significant horizontal loading because of the tectonic deformation. And I plot here contours of the mean stress, overall mean stress, and we see indeed that it's higher in the hanging wall than in the footwall. To quantify this better, I'm gonna pick a sediment, start seaward at point A, crosses the trench at B, and enters the wedge at C. And we're gonna follow the stress history or the stress path of the sediment in a set of axes that has the mean stress in the horizontal and the dewatering stress in the vertical. The friction failure line is here in black, and we see the stress history of this point. And we have an increase in mean stress as we go through the trench and continues to increase inside the wedge. So what we would expect, even from the poroelastic theory, is that this will generate overpressures. And indeed, we find here a continuous increase in overpressures throughout this path. What I want you to notice is that the onset happens here seaward of the trench, and that's because the tectonic loading increases horizontal stresses further out from the trench, even though the seafloor there is flat. So there's no change in vertical, but there is change in horizontal. That's why we see a change in mean stress and onset of overpressure. Now let's go back to this cross plot of our stress path and point out the fact that not only mean stress increases, but also the deviatoric stress increases. And actually it increases a lot faster than the mean stress because we kind of like go quickly towards the frictional failure line. And a way to more dramatically illustrate that is to plot the ratio of shear stress to shear strength, which is how close we are to frictional failure. And when this ratio is blue, it means that you're down here, really far from failure. You have no shear in your system. When it's 1, you are at the failure line. So we see that we are very low values out here, the uniaxial value. Everything in the wedge is failing, and we increase or change between these two states really quickly in the trench area. So why would we care about this fast change when we're talking about overpressures? Where if you believe in poroelasticity, you wouldn't care, because poroelasticity doesn't care about deviatoric stresses. It says every step in mean stress creates an equal step in pore pressure, assuming the BOS is 1. But in reality, there are several observations from mud rocks, including offshore deep mud rocks, that the application of shear generates overpressures. And I have here, as an example, a triaxial undrained shear test on one of these materials. What we do is we start out here, we compact the material up to a level of 60 megapascal, then close the valves and increase the vertical stress to basically increase the differential stress in the system. So again, poroelasticity would tell you the effective stress won't change, right? Every change in the applied load would be the equal change in pore pressure. However, in reality, we see that the effective stress is decreased, and when the stress is decreased, something else supports the applied load, and this something else is the shear-induced overpressures in the specimen. And these are very important here. They're actually half of the externally applied load. So going back to the schematic, we have an increase in the horizontal stress because of the tectonic loading that increases the mean stress, mean-induced pressures, but it also increases the shear stress, and this adds shear-induced pressures. And I quantify this out of results from our model in red here, and we see that the shear-induced pressures increase rapidly in the trench area and then continue to increase inside the wedge. So to take this a step further, we've actually mathematically described how the overall change in pore pressure can be identified as a change in mean stress, as overpressures induced by the change in mean stress, by shear-induced pressures, and then with pressure dissipation. And the mean-induced pressures depend on this pressure coefficient here in green. The shear-induced ones, they have this pressure coefficient in red. And these coefficients are really important because they're basically telling us what part of the applied load translates into overpressures. They depend on material parameters such as friction angle or compressibility, but they also depend on your initial stress state, which is porosity and the shear in the system. And this part here is fairly important, so I'm gonna dive a little deeper into that. So I'm cross-plotting here these pressure coefficients that again define how much overpressure we're generating with the shear stress ratio on the horizontal axis. What the shear stress ratio represents is the level of shear in your stress state. So when it's 0, it means there is no shear, so we're down here. The frictional failure has a constant value that depends on the friction angle. In my simulation is 0.91, but it could be 1.2. I mean, it's not like a gold number, this one, but it is constant during the critical state. And then it has all values in between. For example, there's another constant value for burial. So as we go from left to right in this axis, we're basically increasing the amount of shear in the system. We're going closer to fail in frictional failure. And I start here with a green line, which is the friction coefficient for the mean induced pressures. And this is pretty much horizontal through unity. So what this means is that the mean induced friction pressure coefficient is independent on the preloading stress state. So it doesn't matter whether you start at uniaxial burial state or at a very high friction state, you will generate overpressures that are equal to the change in mean stress under any circumstances. The shear-induced pressures, though, are completely different. And I add here the red line, which is the pressure coefficient for the shear component. And we see that it changes dramatically as we go from left to right. So as we increase the amount of shear in our system. So for example, if your initial state before the application of the loading increment is uniaxial, this means you will generate overpressures that are half of the applied shear stress. If your stress state is close to failure up here, you will generate pressures that are 8 times the applied increment. So this coefficient is really sensitive to the preloading stress state, and it can be a factor of 20 or more between uniaxial and critical state. And the exponential form of this relationship here makes the loading path also very significant. What do I mean by that? If you are experiencing burial, so you are along this line where your stress ratio is constant, so you're always at 0.23 here, you will always generate half the amount of applied stress. Doesn't matter if you are under 1 meter or 1 kilometer of dirt, and doesn't matter whether you add 1 meter or 1 kilometer of dirt above you. It will always be half the applied load. In contrast, if you have a path that increases gradually the shear in the system, every increment will bring more and more overpressures, and they will actually be exponentially more. So that's really significant, and it will generate a lot more overpressures at the end. That's something that is important for areas where the stress state changes, such as near salt or in thrust belts, and that's something that poroelasticity is not able to include. And actually, if you look at this path here, is pretty much what we have in our system for our sediment. Remember, the sediment was starting seaward, was consumed through the trench and into the wedge. There's a fast increase in the shear in here, and this leads to this really rapid increase in overpressures in the trench area. That's why this fast transition from low shear to high shear is really important for the pressure generation. So just to summarize what we've seen so far, we have a change in loading that increases the mean stress starting seaward of the trench and with a constant rate almost throughout the subduction path. And we have shear that onset seaward of the trench, and they're really fast increasing in the trench area. And that leads to overpressures in this area, and then a rapid increase through the trench. Now, because we are doing a transient analysis, we can also simulate how pressures dissipate. And we actually have significant dissipation here. If you see from the black line I added in the plot, these are throughout the subduction process, but they're focused at the trench area. So if we want to add this to our schematic, we have this focused dewatering near the trench. So the fact that we have dewatering means that we can have compaction. And that's one of the significant implications out of this study, is that sediments in the wedge are compacted, or more compacted than the footwall. So I start here with the plot of porosity contours. I take a vertical profile and I plot porosity with depth. The red line is the profile through the wedge, green is at the footwall, and we see again this offsetting in the physical properties in the porosity between the two. If we want to circle back to my motivation slides, this is pretty much what has been observed in the field. And so the key here is that we're now seeing a hydromechanical explanation why we have this contrast, that we have a tectonic loading that wants to induce compaction, but also we have dewatering that allows this compaction to take place. Another significant implication of the fact that we have rapidly increasing overpressures is for the strength of the décollement. Now, the strength is a function of the effective normal stress to the décollement. And effective means we have the total minus the pore pressure. So in areas where pore pressure increases, we expect the strength to decrease. So indeed, I'm plotting on the figure below the vertical effective stress in the left axis, the corresponding shear stress in the right. We see that even seaward of the trench, overpressures increase, so we start seeing this decrease in strength. It reaches the minimum value in the trench area, and then it takes 40 kilometers to actually reach the initial level before keeps increasing. So we have this weakened décollement zone that basically starts seaward of the trench and persists for several kilometers inside the wedge. We've done some parametric analysis that you can find at the paper, and basically, if we push faster, so we have faster subduction rates, or if permeability is lower, this would both expand and amplify this weakened décollement zone. Now, I wanted to sort of take this a little bit at a little higher level. From our simulation, we see how porosity evolves during the subduction path. So we can actually calculate how density evolves and how the compressional velocities change. And in the figure below, we can also get an understanding of how the elastic moduli change throughout the subduction path. At the same time, we've seen that the effective stress is decreased. So these sort of quantifications can help us look at a high level at the criterion for slip, which is here. We want the modulus to be higher than Kc, which is a function of the normal effective stress, and then this weakening, frictional weakening coefficients that I'm not going to touch. So what we know is that the effective normal stress is decreasing. That keeps Kc low. On the other hand, the elastic moduli are increasing. That's because of the compaction that is taking place. So overall, we see conditions that would favor stable slip in the shallow parts of the subduction zone. So what does this mean? Again, at a high level, we have overpressures that start seaward of the trench, and that creates a weakened zone over here that would promote the development of protothrust zones. We have a weak overpressure interface that is basically an area that allows or promotes creep and slow earthquakes. However, this is a weak interface that would also allow the propagation of large slip from higher events deeper. So it's not like a one-way conclusion. One question you may bring up is, okay, you've showed all these models, but everything is nice and continuous. So, but in reality, there are faults in these systems, and faults change both drainage and the state of stress. So this is actually the doctoral research of my student, Graciela. And I have here a few slides just to show what she's doing, and I'll maybe invite her to give her a talk on her results. So I'm gonna play a movie here of her system. Again, is a subduction simulation where we move this backstop. The contours are gonna be principal stress ratio, which is representing the amount of differential stress. Blue is uniaxial, and then orange would be a compressional failure, Coulomb failure. You're gonna see a pattern where she's developing spontaneous faults, but every time we have Coulomb failure, and then the faults open, and then we repeat the pattern, and again, Coulomb failure here, the faults open. So again, 3 snapshots out of that movie, just to make a couple of points. The first thing we see is that once the faults are generated, this differential stress is decreasing. So in a sense, if you're gonna link to the previous parts of the talk, we were up here, but now we're actually getting inside, far away from this frictional failure, because the faults are weak and they decrease the differential stress. Another high-level observation here is that we have this heterogeneity in the upper plate because of the presence of these weak faults. And then some other things we're trying to do is we're trying to understand the formation patterns once the faults are gradually generated. We see that we have these blocks that are formed with the back thrust and the forward thrusts. And these blocks are basically areas of focused deformation. And to quickly highlight that, I'm just taking here a horizontal profile. And if we look at this wedge here, there is a local decrease in porosity shown in blue and a local increase in the mean stress because this is a location of focus deformation. So more on this again, you should ask Graciela. I'm gonna start summarizing here. What I showed is we have hydromechanical large strain evolutionary models that incorporate realistic material behavior and couple this tectonic deformation, porous fluid flow, and compaction. We see that we have a stress change from burial to frictional failure, and that increases both mean and differential stresses. The mean stress drives at almost a steady rate the increase of overpressure, starting seaward of the trench and continuing into the wedge. And then the shear stress has a significant contribution at the trench area. So what we want to keep out of our results is that we have overpressures that increase rapidly in the trench area. We have overpressures that result in a weakened décollement that onsets seaward of the trench and continues for several kilometers landward. And finally, we have fluid expansion that is highest at the trench, and this is allowing compaction and increase in the elastic moduli in this zone. Last but not least, I'd like to acknowledge my co-authors. One was a student at UTIG pre-pandemic, and she did all of the painstaking simulations. Demian has helped me over the years to better understand the whole temporal and spatial nature of the subduction zones. And Peter, who's always pushed me to think outside the linear engineering thinking and try to solve bigger problems. Thank you.
Thanks, Maria, for the great talk. We have plenty of time for questions.
So when you think about the overall role of the complicated mechanics and the fluid transport, and then you compare your model results with a simple sort of critical wedge model, right? How can I think about the effective role of the fluids in terms of, say, a friction coefficient that's variable along the interface, right? Is that a way to understand how sort of tectonically, a wedge that includes those physics does different things than a simple critical wedge.
When you say friction coefficient, you mean at the décollement or inside the sediments?
Well, kind of both, right? But where does it matter most, right? Can I get away with an effective variation of friction along the décollement, or is it really making a huge difference in the medium itself?
So if I understand your question, you saying, oh, we could vary the friction angle along the décollement and so come up with like a similar decrease near the trench and gradual increase. Is that what you're asking?
Yes, not because I want to necessarily do that,
No,
but I want to get a feeling for the physics of what this does effectively.
So if we were only to focus at the décollement, you could say that could be a proxy. However, it's not just the overpressures is not just affecting the décollement, it's affecting the whole wedge, the whole subduction process in a sense. And we see that if we actually quantify this change in stresses and what they mean for pore pressure, then we understand better what happens with fluid flow or what happens with compaction. So if we're just modeling the frictional change at the décollement, you wouldn't be able to quantify or understand that there is more focused dewatering near the trench versus inward.
Right, but so for example, your fault structures, right, they're stochastic, right? Where they form is to do in nature with heterogeneity, in the computations with inaccuracies.
Yeah.
So of course you can't get the same sort of description from a continuum approach. But in terms of, like, say, the average topography or something like that on the wedge, how do I see those effects you just alluded to?
Topography is because topography depends both on the strength of the décollement, but also on the strength of the materials, right? And even if we keep the strength of the décollement the same, overpressures locally vary the strength or the effective strength of the sediments, and not just in the whole wedge, but like they vary quickly. For example, near the trench, they vary with the less rates inside the wedge. So from that point of view, I think I don't see how you would translate all of this in one change in friction angle, but I don't have an answer of what is the contribution to topography either.
Partly to follow up on Torsten's question, or maybe to offer some discussion on that point, right? So I suppose if all you're interested in is like, what's the strength, so you could plug it into a larger scale model, or to think about frictional resistance, that's the primary effect of like this lower plot that you're showing, right? But you showed, for example, what happens to the elastic moduli and what happens to the effect of normal stress. And so I'm wondering if you can talk a little bit about how that might play into how people think about like earthquake propagation or the stability of faulting. It's not a quiz, I'm just asking.
Yeah.
Because I think there's more to it than just, it depends what you're after, right? But if you're just after the straight up strength, then yeah, you could vary the effective friction coefficient, but there's sort of more to it, I think.
Yes, so I guess, and stop me if I'm going down the wrong path, but this drop here is a little bit more like, once you understand it, it would be sort of expected. Okay, we can approximate it by starting to decrease 5-10 kilometers seaward and get a peak minimum, and then we increase it. But I think what Damian was trying to bring in the picture is that what happens in all of these elastic properties, or also porosity, density, depend on dissipation, which is a complicated function of how pressures develop and then how they dissipate. And that makes a difference here, that we actually do see an increase in the elastic moduli, even though we are saying there is a sort of like decrease in the frictional strength. from the fact that we're compacting. Even though there are overpressures, the wedge sediments are compacted because there is the increase in both mean and shear, and because there is dissipation.
Do you think you would see like similar behavior if you had an oblique convergence, or do you think the strike slip faults could sort of significantly affect the pressure and sedimentary behavior?
I think I didn't understand the first part. If
So
we
if
have an
the-
oblique convergence?
Yeah, so if like instead of just purely like that, it was like,
Oh, it's just going down.
yeah, so if you
there
had like
is-
strike slip going in and out of your model, would that like have big effects on like the sediment behavior?
So I think the fundamental response that we are increasing fast one stress component, like faster than the other one, that regardless of the configuration, increases mean stress and also increases differential stress, which is kind of the key in this zone. Possibly if you had a fast increase in overburden because of that deep, the differential stress may not increase as fast, but you will still have shear-induced pressures, and you will still have this local area where you basically become weaker because of this fast increase in pressure. Does this answer?
Thank you.
I have two questions, and maybe you answered the first one already, but for most of your talk, I was thinking about you don't have deformation localization in your models. It's homogeneous, right? But then at the very end, you talk about faulting, right? So maybe you answered this already, but shear localization and compaction localization could behave differently at different scales and obviously affect the stress state. So particular, and I'm not worried about compaction localization, but shear localization, right? It moves you away from your critical state line. So doesn't that, and it can actually occur, you show discrete large-scale faults in the latter part of your talk, but shear localization could also occur throughout the material at small scale, right? Small faults.
Okay.
Doesn't that take away from the first part of your presentation? You know, if shear were to localize throughout the medium, would you still have those shear enhanced pore pressure effects to the extent that you demonstrate that, or would it change the story?
A good question. Let me find this plot here. So I think you made your question very complicated with the micro scale, because in the
Well,
larger scale,
Smaller scale, yes.
yeah.
So you have it at the big scale, right?
In the larger, like if we take the first step,
Yeah.
it's one at a time, I guess. In the first step, to localize the shear, you need to basically go close to friction and failure, and then you open the fault. And so you see this continuing cycle between high shear, we open faults, high shear, we open faults. Whether this would scale down to a smaller scale, I'm not sure if I can answer that. But you would always have to reach some high levels of shear to do any localization, right?
Which I would assume you have in a accretionary wedge, right?
But then if you open small faults that are not able to basically become sort of splay faults, go to the surface, then you wouldn't have drainage paths. So it's gonna be.
It dissipates some of your shear stresses, though.
It will locally.
Right. Locally, yes,
Yeah.
throughout, homogeneously throughout, right? If you assume they're closely spaced, right?
Yeah. But to what extent we actually see that. I'm gonna be careful here what we see, but the faults, if I judge from the larger scale, the faults open, that immediately creates this heterogeneity in the stress state. But then even with open faults, if you see back here, because now you have these wedges that they stop sliding and they're becoming focused deformation, you do increase stresses again. So there is like a cycle that happens. To be honest, I don't know how to answer micro cracks.
We may have a second question yet, real quick. This is much easier, I think. The part that I didn't understand, and maybe I just didn't follow closely enough, but you're saying that within the accretionary wedge, you have this shear-enhanced compaction. Outside, you don't, right? But even in a regular sedimentary basin where you have an increase in sedimentary load and overburden, why don't you see the same effects outside of an accretionary wedge, except everything would be rotated by 90 degrees? So that's the part I missed.
That's a fair question. I think so. In a burial, which is under balance, right? So you create overpressures. You change the vertical stress, that changes the mean stress. It also changes the shear stress. So you see overpressures that we always think of them as scaling to the change in the vertical, but they are also related to the mean because the two are together. And there's also a change in shear stresses that is there, and you're basically in a burial path, your relative shear in your system doesn't change. As you increase your loading, the number changes, right? But it's always the same ratio compared to given your mean stress. You will always follow a path here that the distance from the critical state is always the same ratio. So what we find mathematically is that this would always give you about half of the applied stress. So you do generate shear-induced pressures, but they're always the same amount. And actually, if you read the paper in this sort of paths, you can express them as a function of the mean stress and go back to the nozzle. Everything is like where we have a pressure coefficient and the change in the mean stress. There is an inherent hidden shear stress contribution in there. It's just that because that the ratio is constant, it scales. And I actually found it very fascinating. If you have time to read the paper, it's actually really interesting. And in burial, you can express everything in terms of the vertical stress. But this doesn't mean that anything else is not there. Did I answer that? Yeah.
I have a quick question. Did you explore different initial thickness of the sediment and also the rate of deforming it?
We didn't explore difference in the depth of the décollement, in a sense. We did do 3 cases of different subduction rates. I think it was 1, 5, and 10 millimeters per year. And then also different permeabilities. But we chose 5 as the average because I think one of the pushbacks we got is our sediment thickness were a little high. But then we also had the rate that would basically offset one with the other.
So they don't really change your results significantly?
They do change. They both, let me go here. In terms of the final result, like the décollement strength, they do affect significantly the area that the décollement is weakened. So this is permeability, but you can kind of flip. So this is high permeability or low, and that would be fast, and that would be slow, right? So when you're loading slowly or you have high permeability, your weakened décollement area is very small. You can ignore it in a sense. But when you load fast or you have a low permeability, then you may go like 60, 80 kilometers landward. And then it also affects other things like how fast pressures are generated.
I just have one maybe almost philosophical comment. I mean, this type of model tries to illuminate pore pressure that develops in the thrust system and also rock properties. And one thing I'm always astonished by is, and others in the room can comment, how few direct observations of actual pressure, effective stress, lateral stress there are in thrust belts. And it to me, it's still a remarkable gap after, I don't know, 30 years of ocean drilling. So some of the insights here, and on top of that, it's still really argued about whether the pressure is higher above or below the décollement. And so my point is, I would say there's a lot that is not at least measured or agreed upon. That's it.
Thank you. Very interesting analysis. You certainly built significantly upon what Carrick did in the early 1990s, which I was more familiar with. But if I heard it right, the rates in the models that you did is 1, 5, and 10 millimeter per year convergence rates.
Yes. And
Most of us are interested in subduction zones. That's barely a subduction zone.
that's, I think Damien is smiling. We have, correct me if I'm wrong, right? But we ended up with a pretty thick sediment, and we got criticism that was a little too thick. And so the rates were kind of scaled to address that. That was
but that is the observation of, and Nankai is about 3 centimeter per year convergence rate. So
yeah.
But the issue of your results is indicating we're getting overpressure even at these extremely low convergence
Yes,
rates.
That's
So in terms of the generality for subduction zones around the world, this is sort of the best case for having high, relatively low effective stresses. I mean, for high effective stresses in the real subduction zones, which are going 5 to 10 centimeters per year.
true.
We got a much bigger zone where things are going to be very highly overpressured, and whether they're up at 90 or percent of lithostatic or more is the interesting question. I will say we have an observation from rocks in deeply buried subduction zones is pressure solution as a grain scale deformation mechanism, which is widely expressed in the Gulf of Mexico sediment piles, is a relatively minor part of the story in rocks that have been buried 20 kilometers, which I think are telling us effective stresses for a lot of the burial history were relatively low in most subduction zones. But the last question to close on is, what is your physical picture of the décollement?
Of the?
The décollement. What is the picture that you have in your mind?
Not in the model, right?
Like? Yeah, this is the model.
Yeah.
We got to have a picture of what that black line on all these diagrams means.
For,
What is
for
your
me,
picture of it?
My picture is like a shear zone, is a localized deformation zone that in the protothrust area doesn't even exist, right? So as you eventually localize the deformation enough.
You said shear zone. I like that, but the idea that how thick is this thing? And then we get this issue of, what is friction in a zone which is meters in thickness or more? So, you definitely don't want it to be a planar surface like I can put my finger on.
Yeah. And also, no, that's a limitation of this approach, I guess, that you just assume it to be a frictional interface that also has like very specific flow properties either.
But the description that most people have of subduction zones, they have this picture that it's like a planar surface. In actuality, everything we can see about it is a shear zone. I think there's a very fertile geomechanical thing going on here that is the next direction to go.
I actually take the inspiration. Thank you. Yeah.
Oh, is there somebody else?
It's fine, nothing.
Maria, great talk. I have a question. So like in your model, you showed, and also it is true from other models, from the incoming plate to the wedge near the deformation from the seaward of it is a transition of the stress direction, largest principal stress transitioned from like vertical to near horizontal in the wedge. And however, if we think the dip of the faults are indicative of the stress direction, we do not observe a significant difference of the dip of the protothrust versus the thrust faults near in the wedge near the deformation front. I do not know if you have some comments on that. Is that only the stress rotate to that close to in the wedge that we start to see fault, or why is that?
Unless I don't understand the question, the dip of the faults would depend a lot on the intact sediment properties.
Right, it's like, it's related to the, also related to the the direction of the largest principal stress, and also the internal frictional angle of the material.
Yeah, so I was highlighting the internal friction angle there. So, yeah, I'm not sure. I need to.
I can show you some images.
Yeah, I understand. But I think I understand the question. And in the protothrust area, you mainly have an increase in horizontal stress, right? Even though it's not large enough to overcome the vertical yet, it's still an increase in the same direction.
Right, it starts to rotate, right,
Yeah.
the stress direction, but when we look at the protothrust, those protothrust above the proto-décollement versus like the real thrust faults within the wedge, we do not observe like a huge difference in their dip angles. So yeah, I find that a bit curious. I can show you some images in the afternoon.
Okay, but yeah, if your internal properties though are the same, I don't see how much difference you would see, but.
Great talk. I have a follow-up question. I mean, people have talked about different mechanisms already here, and thinking about the delayed compaction, especially in under-thrusting sediments, you could have higher pore pressures, but for example, as Julie Morgan showed already in experiments about almost 20 years ago, is that you could also have some diagenetic effects that prevent porosity collapse. Are these indistinguishable kind of mechanisms such that you could retain your porosity due to pore pressure and a stronger rock framework, or can you actually tease them apart when you're looking at kind of a margin-wide model?
I don't know if you could do them, like if you could just linearly separate them, but I guess what this offers an explanation without any diagenetic effects.
Yeah.
And when you add diagenesis, you change the frictional resistance, you add cohesion. So that's a different.
Yeah, you have a cohesion, you have a certain
right?
threshold where you start forming when you exceed the strength
Yeah.
of the matrix. Yeah.
So that would then you would need to overcome that cohesion to decrease the porosity. But I agree, this is not the full picture.
Yeah.
But I guess we're trying to offer some explanation. But actually I think in the very shallow parts, especially if you're overpressured, you're not in the region that you will start seeing cementation yet. So you are high pressures, low effective stresses. So anything we discuss, I don't think you can claim the same when you go deeper, but it's more on the more shallow parts. It's not hot yet. You have high overpressures, low effective stresses. So this framework of critical state applies.
Yeah. Thanks.
Can we take a quick online question from Alejandro? Alejandro, can you unmute yourself?
Hi, Maria. This is Alejandro. Thanks for the talk. I know you have thought about this, so hopefully I'm not pushing you on the spot. But so the assumption is that the sediments that are entering the trench are uniaxially loaded, normally consolidated. But if we consider that those sediments can be over-consolidated, let's say due to creep, what will be the impact of that for the pore pressure prediction of the trench and let's say the strength of the décollement?
I guess that would depend on your level of over-consolidation, but you would see, if you're over-consolidated, means you're inside the yield surface, so you would see some sort of elastic response possibly first. I do think that the loads, the stress paths that we're experiencing here are high enough to eventually bring you into a normally consolidated state and then start following the path we're describing. But you would have an initial elastic path.
Okay, let's thank Maria again for the interesting talk. So if you want to join for the lunch, please meet at 11:45 in the lobby.
And if you have any suggestions or comments, I'm here all the time. You can meet. Yeah.